on Smale spaces in zero-dimensional scheme. Thank you for the introduction, and thanks again for allowing me to give a second talk in your seminar. My background is in operator theory, I would say, and operator algebras. And in fact, in the interplay of operator algebras and dynamical systems. And this talk, the stuff that I'm gonna present you today is really about the dynamical systems I was mostly interested during my PhD times. Smale spaces. These are hyperbolic dynamical systems of topological nature, and I was trying to understand analytical properties of operator algebras encoding those dynamical systems, and immediately, well, not immediately, but after working a lot, I realized that those analytical properties were related to dimension theory of Smale spaces. So that's what I'm going to talk about today, and it's not going to have operator algebras. Maybe some brief mentioning at the end and some ideas. I have several examples of Smale spaces, and let's get into it. One of the first examples, or maybe the first example, is Smale's horseshoe. Now there's a formal way of defining the horseshoe, like on the sphere, on the wandering part of self-map on the sphere, but here instead, very briefly, you can view it as the following map. You take this rectangle, and then you have a diffeomorphism that stretches the rectangle horizontally and squeezes the rectangle vertically, and then you have this thin stripe. Now you form it in the shape of a horseshoe, right? And place it above the first rectangle in a way that you still have something left, as well as you have this arc. Okay? And then you repeat the same process. And therefore, you start getting these shapes. And then you can do it infinitely many times. Now, you can start discretizing, because this is somehow a discretized process. You can label the bottom one that I have here with red with 0, the upper stripe with 1, and therefore this thinner stripe will correspond to 0, 0, whereas these will correspond to 0, 1. This one will correspond to 1, 1, whereas this will correspond to 1, 0. Okay, and this can keep going, and you can create infinite words eventually of 0 and 1s. Now you can consider the inverse of f, and then you will have a horseshoe which is vertical to the picture. Okay, so you rotate it 90 degrees, and you repeat the same process. And now, if you take the two limit sets and intersect them, like this limit set and its inverse, then you end up getting this kind of pictures here, okay, transversal intersections. Now, this is a counter set, and it is conjugate, topologically conjugate to the full 2 shift with 0 and 1 words by infinite words. And it's chaotic and a dynamical system in the sense that it's sensitive in initial conditions, you have like many periodic points of period n, like 2 to the n, and the union is dense in X. Okay, so this is really a Smale space. What a Smale space is, you need many periodic points, dense in many periodic points, and transversality of two directions. But if you apply the dynamics, one direction will get contracted and the other will get expanded. Okay. That's a zero-dimensional example of a Smale space. A non-zero-dimensional example is, of course, hyperbolic toral automorphisms. Here I picked the slope to be the golden mean.
So in every point, the expanding and contracting.
Yes, in every point. You can relax this, what you said, and to have it in dense in many points, but then you go to some other dynamical systems that you call synchronizing. So you have like Smale spaces, you have finely presented systems. I can explain a bit more afterwards. Then synchronizing, where you have this product structure almost everywhere. Okay. Yeah, hyperbolic toral automorphism. This is just one example, as we know. I mean, you can create so many examples. The way we'll do it is you consider the two torus as the quotient of R2, and then you consider this integer, this matrix A with integer entries of determinant 1, and then it gives you a diffeomorphism on the two torus. Then the picture is the following. You have the two torus. You pick any point on the two torus that I labeled here as Q0 because you go to that point and that's the tangent space. And then the tangent space decomposes into the direct sum of the eigenspaces. And one eigenspace that I have here with green, the Vs, is the one that corresponds to the eigenvalue theta squared, and it happens to be greater than 1. To theta to the minus 2, which happens to be smaller than 1, and the Vu, which corresponds to the eigenvalue theta squared, and happens to be greater than 1. And this means the following. If you apply the diffeomorphism, I should have written here not f, but phi here in this picture. If you apply the diffeomorphism, then this point will move somewhere else, probably in the torus, and then you will have the other tangent space. And this vector will be contracted by theta to the minus 2, will be shorter, whereas the Vu, the unstable vector, will get expanded. Okay? So imagine if you iterate it many times. It gets like very, very long, this vector. Now, if you project down in the tangent space on the torus, then a very long vector will start wrapping around the torus. Okay? And in the limit, at the infinity, it will wrap densely because the slope is irrational. What else? So, yeah, contraction and expansion, and moreover, you can see that these unstable and stable sets, if you take the product of those, they will give a neighborhood around the point, a rectangular neighborhood. It won't be a disk, okay? rectangular neighborhood. And we will come back to that later on. Now, here I bombard you with a definition of a Smale space. It is what it is, but it works. Okay. The first time I saw that, I was like, wow, what's going on here? Yeah. But a Smale space is really a compact metric space with a homeomorphism that allows you at every point to define coordinates. Okay, so you can find neighborhoods that decompose into two sets. And if you apply the dynamics, one of the two sets will get contracted and the other will get expanded. The first bullet point really tells you the existence of such a local product structure around every point. And here you have some in an axiomatic way. So you try to find a common ground for the horseshoe and the hyperbolic toral automorphism, all right? A zero-dimensional object and this nice smooth object, and try to put it in the topological setting. And the bracket is you take any points x and y which are sufficiently close, so this is a uniform constant, and then you can create another point, the bracket of x and y. I have a picture later on to show you what I mean by that. In here you have some associativity of the bracket, how you can take brackets, it's really that, and compatibility with the dynamics if x and y are close enough. Okay, so in Smale spaces things work nicely if you're close enough. If you're far away, if you consider points that are far away, if you try to apply the bracket map, you're gonna get wrong assumptions, wrong results, simply because you can, in this picture, you can have these unstable sets being long enough so they wrap densely enough in your space, and then you might have 2 points, let's say here, one here, and another for a return of this stable set, which are in the space close enough, but dynamically they're far away. Okay, so you need to be careful when you can define the bracket map.
You might try to extend the local bracket for losses to global. I think it is open problem. If you can do it, then it is toral, it's an element. And the question whether there exists a loss of information on other manifolds.
Yes.
It is equivalent, I think, possibility to extend.
But there are also cases that you will get wrong results.
I just don't analyze possibility to define and that is not unique.
Yes.
I just want to common possibility to extend the local continuous.
Yes.
This is very delicate.
Yes. Thanks. And moreover, you have this existence of local product structure around every point, and then using this bracket map, you can make sense of a set that we call stable around x, small enough, so you pick some epsilon, and an unstable set. And if you apply the dynamics phi and phi inverse on the stable and the unstable respectively, both will contract. Now, if you apply phi inverse to the unstable and contracts, means that if you apply phi to the unstable, it will expand. Okay? And you want this contraction to be somehow in a uniform way. Okay, right. So here's a picture. It helps a lot. Yes. You take any point in your space X, and let's assume that the vertical direction is the unstable direction, and the horizontal is the stable direction. And now, whenever you take point Z in the stable direction and point Y in the stable direction, and both are sufficiently close, then you can take the bracket map, and the bracket map will be another point. Okay? The bracket map really gives you local coordinates. As you get in a Euclidean space. Now, in a Euclidean space, you can have global coordinates. Here, you can have local coordinates around point X. And
my comment for concern higher dimension. And also
yeah,
on the toral.
Do I understand correctly that you take your y and you draw through it unstable manifold and
exactly.
stable in this
Exactly.
section where you
Exactly. So around every point in your space, you have stable and unstable manifolds. And as Martin said, you pick, you go to Y, and you take the unstable manifold, a small piece, and you go to Z, which is close to Y, and you take the stable piece, and these will intersect at one point only, okay? And that will be the point. Now, if you apply the dynamics, this rectangular shape, the positive dynamics, like positive time, this will get squeezed and expanded, okay? And if you apply the inverse dynamics, the opposite thing will happen. Now, another thing to note is that these pieces, like these directions, do not need to be one-dimensional. Okay, they can be of whatever dimension. But people think of rectangles because it's easier to picture, to depict, but also if you try to do computations with the bracket map, thinking about rectangles only, like these two-dimensional objects, it works.
David does not.
update later of laws.
Okay, so examples. Non-wandering sets of Axiom A systems. Subshifts of finite type. Groups with expansive automorphisms and some other property that gives you this local product structure.
But when you're talking about groups, so in the definition you had just one homeomorphism. So here,
No, the group is the space.
The group is a space and you have an expansive automorphism.
so you're
Yeah, like examples from dynamical systems of algebraic origin, like Lind and Schmidt dynamical systems. Aperiodic substitution tilings, fractals like GSS from Elektroshevitz, similar groups, so on.
The dot. The dots.
Yeah, I have it here, and also different morphisms. Yes, exactly. Now, let's see another example. As I said, topological Markov chains. You get an n by n matrix, entries 0 and 1. Let's make it simple, okay? No row or column, and this matrix consists only of zeros. And now we have the space of allowable words. Okay, so you have by infinite sequences. So here you need bi-infinite sequences because you work invertible dynamics. And xi can be concatenated with xi plus 1 whenever the matrix allows you to do so. You can put a metric, in fact it's an ultra metric. It really measures for how long two words are agreed from the center. Okay? And the bracket map here is the following. You can bracket x and y are by infinite sequences, and you can bracket them whenever they are 1/2 close, so whenever they agree at the middle part. The bracket is the following of x and y. You take the left part of y and the right part of x, and you concatenate. And you can do this because they agree at 0. The left shift map, you shift to the left, it's a homeomorphism, and it expands and contracts the stable and unstable sets that are defined from the bracket map by a factor of 2. Now you might think, we have a safe space here, why care about the bracket maps and put more structure and make it more difficult? Well, this is an intrinsic structure. It's something more that the space already has. It's not that we put something artificial. And having a bracket map, as I said, really allows you to employ ideas from differential geometry in the study of Smale spaces, since you have local coordinates. Another example, the dyadic solenoid. Take the unit circle with the arc length and consider the doubling map. This is an expanding map in the sense that if you focus on points in the circle which are close enough and apply the doubling map, their distance will go further away. Okay? How do you construct a Smale space from such a map? Now, this map is not injective. And we want to create invertible dynamics. And the way to do this is by taking inverse limits. Therefore, we consider the space of infinite, not by infinite, of one-sided infinite words, where the symbols are in the unit circle. And now you can and z1 squared is equal to z0, z2 squared is equal to z1, and so on.
Inversely.
Inversely. And you can now metrize a nice metric on this space is given simply by taking two such words, measuring the distance in each entry, in each coordinate, and then the further you go in the words, the less important the distance it becomes. You put some weights here, okay? So it's more important what happens in the first entries, coordinates, and then less important. Homeomorphism now, produced by this double map by G on the inverse limit, is simply having G acting on each of the entries. And if you allow G to act on each of the entries, you're gonna get that. It's really a shift. So you get G0, G at G1 is equal to, G at Z1 is Z0, and so on. So you shift. And the inverse is really by killing the first entry of your sequence.
So if you continue the sequence also in the opposite direction, just by operating squares, does this become similar to this formula becomes similar to the previous example, right?
If you continue the
So if you consider instead of
by infinite.
one-sided, you can consider two-sided infinite sequences just by iterating taken square. And then since the formula for the bracket becomes similar to the previous example.
Ah, to the bracket, yes. I thought this part, yes.
It's O2.
Excuse me?
It's subjective.
The map.
Yeah.
The W map.
So the G hat?
Because this is subjective. Now, if how do you define the bracket map? Well, you need to consider points in this inverse unit, like sequences, which are 1/4 those. And then if you apply, yes, so they are 1/4 closed, and this map now, the G hat, contracts and expands by this factor of 2. And the bracket map is as follows. So since these sequences are 1/4 closed, it means that the first entries are 1/4 closed in particular. And therefore, there is a unique rotation, like positive or negative, so that x0 is y0 times this rotation. Okay, that's why you choose 1/4. You find a unique rotation. And then the bracket map is really multiplication of the sequences, coordinate wise. Okay. Now, the talk is about dimension theory of Smale spaces, and what do I mean by dimension theory? Well, several fractal dimensions that we saw in the previous last week's talk. Okay, and in fact, I was planning to give another talk, but I thought it was a good chance to talk also about dimensions after the talk last week. We will deal with Hausdorff dimension, the box counting dimension, and well, I guess no special introduction is required here. And the Schwarz dimension, it was also briefly mentioned last week. Now, it's a dimension that captures homogeneity of your metric space at every scale and is related to by Lipschitz embeddings in Euclidean space of your metric space. Whenever this Schwarz dimension is finite, you can have a by Lipschitz embedding of some snowflake version. And in fact, it's a sufficient and necessary condition. In general, you have that the topological dimension is smaller than or equal to the Hausdorff, the box, whenever this exists. So I should put here like the lower box and the upper box dimension. And the Schwarz dimension majorizes all. Now, the one observation is that whenever this Schwarz dimension that I haven't really defined it, I can define it if you want, but think of it like as this. So it is finite whenever there is a constant k, so that every ball in your metric space of radius 2r can be covered by k balls of radius r. It's a doubling condition. Okay. Now, another thing that we will focus is Ahlfors regular measures. These are Ruelle measures, so that every ball of radius r has volume r to the s. Not on the nose, but in a uniform way, in the sense that there are constants C1 and C2, positive constants, so that the volume of this ball is greater than or equal to C1 times R to the S and less than or equal to C2 times R to the S. And in fact, whenever your metric space admits an Ahlfors regular measure, S regular measure, then all the dimensions agree and are equal to S, and the measure mu is comparable to the S dimensional Hausdorff measure. Okay, please, you have any questions? And why should we care about Ahlfors regularity? Well, because of, let's say, dimension theory. It's a canonical way to compute dimensions, but as we have seen from last talk, not all metric spaces have the box in Hausdorff dimension equal. In particular, not all metric spaces admit Ahlfors regular measures. Now, what is interesting though is to know that a topological space admits a metric and a measure, so an Ahlfors regular metric measure structure on it. Okay? Because in fact, if the measure is compatible and the metric is compatible with dynamics. And in fact, then you can really start doing harmonic analysis on the metric measure spaces. I have given a talk about the first part here last time, and you can do analysis on limits of Kleinian groups, for instance, or on foliations of Markov chains, stable and unstable foliations of Markov chains. And this is the part that I was going to talk about, and then I decided to talk about dimension theory. You can also, using Ahlfors regular structures and then fractional calculus, study Monch-Kantorowicz metrics on metric spaces, like metrics on the space of Borel probability measures on metric spaces, and get closed formulas. All right. So Ahlfors regularity, the Bowen measure. Okay, so I'm going to move on that. The Bowen measure is the asymptotic distribution, basically, describes the asymptotic distribution of periodic points in a Smale space. And how do you define it? Well, these are the periodic points of period n. You know there are finitely many for each period. And therefore, you define this average. And you then know it has a unique weak star accumulation point. That this is what we call the Bowen measure. Now, this measure is invariant under the dynamics, of course. It's a probability measure, of course. What is not obvious and requires proof is that it maximizes the topological entropy and zero. Whenever you assume some recurrence. On a hyperbolic toral automorphism is the Lebesgue measure. On topological Markov chains is the Parry measure, is the measure that is built from transition probabilities between vertices on a finite directed graph. On the dyadic solenoid is the Haar measure. Okay. And in fact, on all the abelian groups with expansive automorphisms that have a Smale space structure, the Bowen measure is the Haar measure.
For general amenable groups, is it?
What?
For general amenable groups, don't you have this?
That you have a unique star accumulation point? Yeah. Yeah, but do you know that maximizes topological entropy?
This I don't know.
Yeah.
It can be constructed in this way.
Yeah, sure,
Yeah,
sure. Of course. So the bound measure is called often the measure of maximal entropy. It's measured as a measure theoretic entropy, and you have a variational principle. Okay, that there should be a measure that realizes the topological entropy, which is the supremum, or the theoretical measure theoretical entropies. The bound measure realizes that.
It's interesting that for complex polynomials it's a measure, harmonic measure of algebras. And you go there and kind of discovery for me at least. Maximal is harmonic, so it can be treated without any dynamics.
But treated in what sense?
Consider like the half of dimension is equal to 1.
Ah, yeah.
Same as with assume always there is some dynamics. But this meantime, my current movement without any dynamics. Complement of complex.
Yes.
Dimension is 1.
Yeah, you can find instances of this measure in several contexts, also in continuous, not discrete dynamics, but also in continuous dynamics, like flows and on negatively curved manifolds. And
But it is harmonic, it shows this dynamical theorem is completely general.
yeah. So I'm gonna show you how to prove that this measure is Ahlfors regular for some special metrics on any Smale space. Now, for this, we will make use of so-called Markov partitions, and these really provide a combinatorial model for Smale spaces. One of Bowen's theorems is the following. You start with a Smale space, and then you can create a subshift of finite type that sits above the Smale space, so that the Smale space is a factor of the subshift. And by that I mean it's a quotient, and the quotient map intertwines the dynamics. Now this map is also nice. It is injective on a dense, in a big set, on a dense G delta set. Moreover, it is uniformly finite to 1. The cardinality of the preimage is uniformly bounded. And the map at the measure theoretic level is an isomorphism. And then this allows us, yes, it's an isomorphism. And then, whenever you equate both spaces with the Bowen measure. So in this Smale space, the Bowen measure is what I showed you before. If you equate the subshift, which is a special case of the Smale space, with the Bowen measure, then this is the parity measure. Okay? So the Bowen measure generalizes the parity measure.
Why can we take sigma m and equal x?
What? No, as
It's a shift, right?
yes.
Same ratio.
I'm not saying that x and sigma are like at the topological level equal.
No, what
To
is
within instead they are, which
Yes.
they didn't are.
Yes.
And this is theorem about Markov partition.
Yeah. So the idea is the
No, I don't understand it either. For a mixed Smale space, there is a mixing space.
it is subshift.
Okay.
Ah.
Thanks. Okay.
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 Yeah. No.
Okay.
Subshift of
Subshift.
finite type.
Okay.
Yeah. And now we have that the topological entropy of the Smale space is equal to the topological entropy of the shift space because of this variational principle and the maximizing entropy part of the bound measure. And here we can use Gerontogiannis theorem to compute the entropy. Okay, so that was how bound computed the entropy, which is a very neat way, awesome way. Okay, so these are most definitely not Markov partitions.
Sorry,
But,
to share. So the previous so lambda max is will be some algebraic number.
Yeah, algebraic number. Yeah, it's the highest eigenvalue that you get from the Gerontogiannis, and it's greater than 1 because of irreducibility, in particular mixing property of.
So particle means that the entropy of this mixing Smale space is a logarithm of algebraic number, right?
Yes, yes, exactly. Now, I'm going to show you how to start with Markov partitions and create finer and finer Markov partitions. Now, these are most definitely not Markov partitions, but I am not very artistic, let's put it that way. You start with your space.
Satisfying from the local product structure.
Yeah.
But let me add one interesting fact. When you don't assume local product structure, you have hyperbolic, then you can extend your hyperbolic, at least when you do some only differential, then you can always extend.
In a neighborhood.
And your Markov partition
Can almost extend.
is partition of a neighborhood, of a small neighborhood.
Yeah, you can also extend it to around with adaptive metrics.
Just repeating the proof of existence. You don't need even to assume this local product structure, and then you obtain something bigger.
Yes. Yeah, in fact, you can have Markov
But it does
partition.
not mean that this extension satisfies the local product structure.
Exactly.
It's not possible.
Yes,
It's
exactly. Yeah.
But local, but the measured product extents you obtain something.
Yeah. For instance, a generalization of Smale spaces, which are like the finely presented generalizations of Reed, they can have Markov partitions, not necessarily a local product structure on every point. Like pseudo all solved stuff.
From measured theoretic point of view, it's sufficient.
Yes.
Markov partitions.
Yes.
Small extent.
So, you partition your space into closed sets, okay, which are the closure of their interior. They're nice enough in topological sense. And you want the overlaps to be small, okay, no more dense. Now you also want them to be behaved nicely in a dynamical sense. That the next pictures will explain how it is. I'm not writing the definition about partition, there is no point in anything. The idea is the following. You apply the dynamics, phi, okay, positive time, and now this is the unstable direction. So these rectangles will get shuffled, but they will get stressed vertically and horizontally get contracted. So that's a picture. Now if you do the opposite, the inverse, you will get the other behavior. This will be a Markov partition whenever you take these two covers now and intersect them. You put one on top of the other and you see only these kind of pictures. So either full crosses, okay, but not these, like these half crosses. If you see these, no, it's not the Markov partitions. If you only see that, most probably they are. Okay, in fact they will be. And Bowen showed that every Smale space has Markov partitions of arbitrarily small diameter. That's important. Okay. Yeah. Now, let's do some approximations by Markov partitions. What is the thing that we want to show is that the Bowen measure is Ahlfors regular. Okay, so we want to be able to estimate the volume of any ball, take it closed or open, whatever, to be able to estimate this. What we can estimate from Bowen's theorem is the volume of this kind of sets of rectangles. Okay? Because if we go back to this, the volume of well, such a set, such a rectangle will be the image under this quotient map of a cylinder set on the shift space. And since in a measure theoretic level these are the same, then the volume of that rectangle will be equal to the volume with the parameter of the cylinder set. And this can be computed. Okay, it's combinatorics. But now we want to be able to estimate this. And this ball is not a rectangle. Now, what we can do is maybe easier is to estimate this from below. Because you can find a small enough rectangle that is inside the ball and then do the estimate. But what about an upper estimate of that? Okay, so somehow we need to construct a method that interpolates balls between rectangles. We would like to do this. If this is your space and you cut it into pieces, and you take some ball here, we would like to know how many rectangles intersect that ball, and all rectangles of size similar to the diameter of the ball, radius of the ball, how many of them intersect at every level, every scale. It can very well happen. That would be easier if the ball had center in the center of a rectangle, but you cannot always have that. You might have like a ball with center at an intersection of rectangles. So this is what we will try to study.
What happens if R1 is not small? What could happen, would go wrong if Rn cannot be small?
The reason I'm taking small, it's not that something would turn wrong, is that what I described here, it wouldn't work for the first stages. I will explain. I will answer your question.
So, but eventually it
Yes.
gets
Yes.
small.
Yes, eventually it will get small. Yes. So the idea is you start with a Markov partition and then you try to refine it. Okay, and how do you refine it? Well, you go back here. Where is it? You start with a Markov partition, you take the forward version of it, the backward version of it, you put one on top of the other, and then you start seeing these smaller rectangles. This will cover your space, and in fact, you can show that this is again a Markov partition. Inductively, you can create a sequence, a refining sequence of Markov partitions. In fact, you can build a tree where the root will be your space. Here you will have, the vertices of the tree will correspond to the rectangles of the first Markov partition. Then you go down, not necessarily diagonal tree, but that's the fastest I can draw. R2, this is again a Markov partition going down, and at the boundary here you have X. Okay? So you take all the infinite paths and you go down to a point. In fact, this bounds quotient map to the path space of this tree. Okay, so each level is a Markov partition. Now, the following interesting things happen. You can control the diameters. That's not super difficult. It comes from the dynamics. You can also control the multiplicities of each cover. The multiplicity is the coloring of a cover, and in fact, this is because of this uniformly finite one property. You can control the cardinalities, so the cardinalities of the covers increase with the entropy. So the cover at the end will roughly have cardinality of e to the 2 times the entropy of the map times n. And what is not obvious is what I call the neighboring rectangles lemma. And this is the important part for Ahlfors regularity. It means the following, that if you focus on any rectangle at any level, okay, pick a small enough rectangle, then you try to understand how many rectangles of that same level intersect the given rectangle that you have. Okay? In fact, whenever you go down, all the rectangles become smaller, so one might think, maybe you have more intersections. Okay, because it increases exponentially. Equivalently, if we define this tree and try to make it into a graph, possibly with some loop, with some cycles, you could say that I draw a horizontal edge between these two if they intersect, for instance. If they intersect, you draw horizontal edges. Now, what I'm saying is that given any Markov partition, taking this tree of Markov partitions, there is a uniform number for the number of neighboring rectangles of any rectangle of any level, which is equivalent to this graph now, not necessarily tree, to have a uniformly bounded degree. And this can be proved, and the essential part is like that you have the Markov property. Okay, it's like memoryless, so you can do inductions, but it's not so obvious. At least, yeah, it took me some time to come up with the proof because it's something that you can see in the two torus, for instance, that this can happen, but in general, we don't have like actual geometry that you can manipulate. Okay, but now having this tree of Markov partitions with a nice properties, can we interpolate a ball of radius r? By interpolating, I mean the following. You pick an r, and you try to see which of the Markov partitions have diameter similar to that of r. And then you interpolate, here maybe you have Rn, maybe you interpolate the ball here. And you want to squeeze it between rectangles. Like find a small enough rectangle inside the ball and rectangles that cover that ball. And this uniform boundedness, for how many rectangles intersect, will really tell you that you have like uniformly many rectangles needed to cover, of size similar to that of R, that needed to cover the ball. But we still have a problem. What if we take X on one of these?
So this bound will give a bound on the Ahlfors dimension?
No, it's related. The bound is something like you take R to the you take R1 and you raise it to 2 to the n plus 1, I think, where n is the cardinality of the first cover to 2 to the n plus 1. That's how many intersections at most that you can have. And this n comes from the following. If you take a Markov partition and you take two rectangles here, and let's say these that do not have a common rectangle that they intersect, let's say this is in R small n, then you try to see n plus capital N. These are smaller rectangles that also cover your space, and so you get something like that. Okay, you try to see how far down the tree do you need to go so that these non-intersecting rectangles will have a neighborhood of created from smaller rectangles that they do not intersect. It's like normality, normal topological space. You have two closed sets and you want to separate them by some neighborhoods. Now the neighborhoods are created from smaller rectangles in the Markov partition, and this n is like the minimum number that allows you to separate for every small line. I can explain more, but it's combinatorial.
So if these rectangles generations deformate, then it is not the case. We want shapes of rectangles in all generations comparable.
No, the shape doesn't matter. That's why
it is not the next rectangles become more and more different colors.
no, it doesn't matter. It's like for any shape, it's for any Smale space. You can have these neighboring rectangles, the uniform upper bound.
Because you are interested in upper bounds.
Yeah.
Because if you just want to calculate dimension kind of similarity in generations, because you have different generations, if you want the same size, you have so-called moral.
Yeah. I know.
It is not.
It doesn't matter.
Having
No, it doesn't matter. It doesn't matter. You just try to see that this
So
graph is.
your rectangles can develop.
Yeah, or whatever. But here's the issue that if you take a ball from these lower dense subsets, and you try to do this, you don't know what's going on. You would know if the ball was inside, the center of the ball was inside here, and then. So the idea is to create an enlargement, an open version of the Markov partition. That's called delta enlarged. First I called it delta fat. That doesn't sound very nice. But it's really fat because it's like in the steak, the fat around the steak. So what do you do? Yeah. What do? You take a rectangle and you go to the stable and to the stable boundary of the rectangle and you attach small unstable parts. You go to the unstable part of the rectangle and you attach small stable parts. Then you take the rectangle completion, let's call it, of this construction, and you end up with a rectangle which is open now and bigger than the first one. Now the idea is to try to create a refining sequence of these delta enlarged Markov partitions, as you have here, but now by open covers. And why would you do that? Because you want to create Lebesgue numbers of the covers. Lebesgue number of an open cover is a number that tells you that L, that tells you that any ball of radius L is inside a set of your cover. And then if you have this, assuming that you do this enlargement in a controlled way so that you retain these neighboring rectangles and everything else, you would be able to do this interpolation. And indeed, this is the case. You create open covers Rn delta that behave like Markov partitions. And a refining sequence, so as n goes to infinity, the diameters converge exponentially. That's easy. You do it, this enlargement, in a way that you do not destroy the multiplicity of the covers, so it's like the actual Markov partitions. The neighboring rectangles at each level is again uniformly bounded. The cardinality is of that order, controlled by the entropy. And now, if you also assume, it's not necessary for 1, 2, 3, and 4 to have Lipschitz dynamics, but if you also assume that you have like some Lipschitz dynamics, either phi or phi inverse Lipschitz or both of them, then you can also control the diameter of the covers from below. Okay? And also the Lebesgue numbers. So you have full control of the space. Alright, but now to be able to compute dimensions, we need. So this is the best that can be done in the general setting of Smale spaces for any metric. Now, to get Ahlfors regularity, you need a bit more controllable metric. Okay? And we come to self-similar metrics for Smale spaces. Artig had shown that expansive dynamical systems admit nice metrics. In particular, Smale spaces admit those metrics. Topological Markov and so the metric is self-similar if the contraction rate, like contraction or expansion rate, your Smale space is equal to the Lipschitz. You have defined it in a different way, but it's equivalent to that. Okay? So if the Lipschitz then constant is equal to the contraction constant. Yeah. The small lambda is the contraction or expansion. The Lipschitz constant. So So whenever you have this, and you act with the dynamics on stable or unstable sets, you act by a multiple of lambda. Okay? So it's an isometry that multiplies by lambda. Isometry. It's a multiple of an isometry by lambda. Okay? So it's conformal in a strong sense, in a uniform sense. And you always have this, so you always have those metrics that give you the same topology, of course. You start with the Smale space, you change, you can construct a metric that gives the same topology, and in fact, with that new metric, you still get a Smale space. You still have the hyperbolicity and local product structure, it's like topological. You still have the hyperbolicity.
Isn't someone called visual metric?
How?
Visual metric. Because there is an illusion when you have expansive mapping of numbers.
Yeah,
You
yeah.
take a neighbor.
Yeah, it is related to that.
Parameters and
Yeah.
you have a graph. And from this graph, you get it with
I understand, yeah.
consecutive covering of parameters. And this graph,
I understand, but
there's a defined metric.
yes, I understand. But yeah, I should maybe mention that Artiga did not construct those metrics in the sense of visual metrics because he didn't show Ahlfors regularity, and
From Ahlfors.
yes. So whenever you have an Ahlfors regular space, you can construct using dyadic decompositions in your space a graph like that, so that the space, the Ahlfors space, is a boundary of the graph. But here we don't know if the space is Ahlfors regular,
I have in mind.
and we should try to construct a graph.
I have in mind Kaczynski and Pilgrim, there is such a good paper.
At the end,
You have in mind.
yeah.
My question.
At the end, through the Ahlfors regularity, this metric indeed will be a visual metric, because it would be related to such a construction at the end.
I'm not special, but I learned this notion, visual metric, and this.
No, your intuition is right.
Kaczynski and Pilgrim.
Your intuition is right. Now, topological Markov chains are self-similar. Indeed, on stable and unstable sets, you act by multiplying by 2 or e to the minus 1 if you want to contract. And this is also the Lipschitz constant of the left shift. Hyperbolic toral automorphism, the metric is not a self-similar metric for the hyperbolic toral automorphism is really the following. So you take x and y on the torus, and you project it, you write x and y in terms of these stable and unstable vectors. Okay, so you change the coordinates, and then you write it as x, you write it as x stable and x unstable. So you take the product metric kind of. Okay, that's with respect to this decomposition that we had here. And this will be a self-similar metric. For the dyadic solenoid, you take x and y, and then you focus on their orbits, the full orbits. You take distances. You take the maximum distance, and you put a weight that comes from dynamics, and then you get that. Okay, and now for self-similar Smale spaces, like for Smale spaces equipped with these self-similar metrics, indeed you can start with any Markov partition in any and each refining sequence that I described, and then you will have this uniform finite clustering property in the sense that I described before. If you take any ball of radius r, then the number of rectangles of size comparative to R will be uniformly bounded. This is what it says, okay, for any point X. And using some other stuff, then you can estimate the volume of all of radius R and obtain that the volume measure is indeed Ahlfors regular. This is the dimension 2 times the entropy over the logarithm of the contraction. Consequently, all the other dimensions are equal to this S. And now, since the matrix, the self-similar matrix, in many situations they are constructed, I would say, in a canonical way. In many situations, in the abstract setting, it's not a canonical way. But if you start with a Smale space that already has Lipschitz dynamics, then the self-similar matrix can be constructed in a canonical way. And you obtain the following. If you start with any Smale space with Lipschitz dynamics, and you assume that the contraction rate in the Smale space is greater than 2 times the Lipschitz constant of the bracket, this is the following. You have the distance of x and the bracket of x and y to be smaller than or equal to this constant x, okay, and you have the same for y as well. So the bracket is Lipschitz, jointly with Lipschitz. And this will be the case whenever you start with Lipschitz dynamics on the Smale space. The bracket will also be Lipschitz. Okay. Then you have this estimate for the Hausdorff box dimensions. And the lower estimate enhances an estimate from Fathy obtained for the lower box dimension, where the first estimate was the entropy over the logarithm of Lipschitz, but now it's 2 times. Okay, so it's closer to that. So whenever the bracket is like 2 times, this is like close to 1, and the contraction is close to the Lipschitz, you see that, you know, all these converts to like 2 times the entropy over the logarithm of the contraction or the Lipschitz, the dimensions.
And then the identity?
Identity we have for self-similar.
What was AX positive?
AX is positive, yeah.
I mean, that all of these are equal.
Yeah, for a self-similar, all of them are equal.
I mean, that the with 2h of 5 over order is.
Yeah, so this will be away, this will be gone, and the small lambda is equal to the large lambda.
In this case, AX equal to 1/2.
Yeah, but no, wait. It's epsilon. 1 plus epsilon. Oh, I think I might have a typo here. Yeah, I don't remember what I have in the paper. Yeah, but this should be gone. I think that yeah, but in the self-similar, it's all right. And some previous results on Ahlfors regularity. Well, you can start with building product measures, Ahlfors regular product measures in stable and unstable leaves. And this is what Mane had done on, for horseshoes to compute the Hausdorff dimension of horseshoes on closed surfaces of C2 diffeomorphisms. The issue there, the thing there is the following, that the stable and unstable sets are one-dimensional, which plays a big role, and then the holonomy maps become by Lipschitz. Therefore, you can take the dimensions of the stable and unstable and take the product. In general, you cannot do that.
I have a paper with Rams and Teresa on
About
the
that.
solenoid.
Ah,
So Ram dimension is one dimension. The other is two dimension. And we also prove how the dimension is constant, the same on sections and it is like it should be. And the key is to prove that this one-dimensional foliation is Lipschitz, which
Yes.
is not, but except only a thin set.
yeah.
So this is our main. And in general, I think it is Ekman and some of the conjecture that it is more general.
Okay.
In the hyperbolic set.
Yeah.
But this is all.
Mm.
For solenoid,
Okay.
I did it with Michal is listening.
So,
So it was started by Schmeling and Partitions.
yeah.
No Schmeling and
I
Hasselblad.
Hasselblad.
There is such a paper.
Yeah, Hasselblad also has
Go and we continue with this. We can
Okay.
have this paper.
Also Hasselblad has some work.
Oh,
Yeah, has some work on
ah.
like foliations, if I recall.
This is all. This is 2010 later. Recently continued.
Now, Pessin also has several techniques for computing dimensions, and in fact, those techniques, I believe, although have that, I believe they can be used to prove Ahlfors regularity, which are different, but for conformal C1 epsilon systems. And so you need your space to be in a Euclidean space for those techniques to work because of the following remark. And to show, to compute this Ahlfors regularity, you need somehow to control the doubling, how many balls can fit inside one ball. Okay. And in a Euclidean space, you have the following volume argument. For every dimension n and constant c, you can find a k so that every ball of radius in Rn of radius r fits up to k balls of radius c to the r. This is what you have in a Euclidean space. And now you have a fractal inside the Euclidean space, you can use this argument for the fractal itself. But for Smale spaces, which are defined abstractly, axiomatically, you cannot use these volume arguments. You don't know if they are in a Euclidean space, like solenoids. You don't know, they might not be. And the equivalent of that, what the Markov partitions allow us to circumvent the need for such a volume argument. Markov partitions, these uniform rectangles lemma, it's like an intrinsic version of these volume arguments. Okay. And also we have like doubling measures, but doubling measure is something weaker than Ahlfors regular measure. Also, you can compute the Hausdorff and Boxkamp dimensions for Smale spaces using a Barreras thermodynamic formalism, but these are not. These will not give Ahlfors regularity. Okay, you need to do something more. And in the last 10 minutes, and here I have a Schwarz theorem that okay, so now we know that the Schwarz dimension for self-similar Smale spaces is finite. Can we embed Smale spaces into a Euclidean space as self-similar Smale spaces to Euclidean space as they are in a by-Lipschitz way?
Even question from old power paper. Can every Smale spaces can be realized in a smooth way, axiom A. It's not precise what I'm saying, but formulated.
So it's so it's something similar question, I guess. Because now we know that you can embed Smale spaces into Euclidean space.
Or smoothly.
How smooth? Yeah. And
from an author.
And whether the embedding of such a Smale space will again be a Smale space, okay? Because there are several moving parts in a Smale space, like about the hyperbolic.
Remember that he proved in a complicated way existence of Markov partitions. Later he gave simpler proof using shadow. His paper didn't prove it, complicated, and he didn't assume smooth something. He defined axiom A. In topological ways and proved it with Markov partitions. So the question was maybe his axiom A was in fact axiom star. A star was in fact axiom.
But I must say that somehow it feels possible that we should Anyway, so in the last few minutes I will very briefly go quantum, okay, and I'm going to the start of the story. Why was I interested in Ahlfors regularity and the house of dimensions of Smale spaces? So, very briefly, one idea, one way to use operator algebras on Hilbert spaces to study dynamical systems is that you can take a dynamical system and represent it on a Hilbert space, okay, in terms of operator algebra. So it's it offers you a representation theory for dynamical systems. And sister algebra, it's a collection of bounded operators on a Hilbert space in a way that it forms an algebra. And you have also the notion of an adjoint, like the complex transpose, the conjugate, and you also have the operator norm on the bound operators on a Hilbert space. You want this algebra to be closed under the operator norm. Here are some examples. And the Gelfand duality says that topological spaces are in direct correspondence with commutative sister algebras. So you have topological space. How do you get a commutative sister algebra? Well, the continuous functions in that space equipped with a supremum norm. Now, if you have a commutative sister algebra, how do you go topological spaces? You consider the character space of the algebra, and this becomes a nice topological space. Now, whenever you have a group action on a space, the equivalent sister algebra is this semi-direct cross product, and therefore you can encode the orbit space of the group action in this algebra. So this algebra is like any element in here can be approximated by finite sums of elements in gamma with coefficients functions in C of x. So it's like Fourier expansions. And these act is Hilbert space. And moreover, if you start with foliations, you can construct a sister algebra of foliations. And so you have operators moving along the leaves. And you can represent it in a nice Hilbert space. Okay. And the cycle through representation theory is that you start with dynamics, you symmetrize the structure into what is called groupoids. It's a generalization of groups where you have partial multiplication only, partially defined multiplication. And then the groupoids, you can represent them as Caesar algebras, like as a collection of convolution operators. And then the Caesar algebras allow you to obtain topological invariants into homology theories, like K-theory. And these give index theorems for dynamics, so you go back. This cycle offers you, through representation theory, offers you a way to obtain topological invariants for dynamical systems. And non-commutative geometry makes the last arrow computable. You try, instead of Caesar algebras, which see only the topological aspect of the dynamical systems, you try to work with finer algebras, Banach algebras inside the Caesar algebras, that see more of the metric or the smooth structure of the dynamics. And just a picture here, you have this torus, and take the point Q0, assume it's 0, so it's a fixed point under the dynamics. And if you see these thin lines, assume they are the unstable, they form the unstable leaf of this point, all right? And it wraps density in the space. And on here, now, you take a stable equivalence, restricted on this unstable leaf of 0. Unstable equivalence means that the points, if you iterate the dynamics forward, will get closer and closer, even if they are restricted to some unstable set. And W and V, and then you have a way to construct a holonomy map. You take a small unstable set around W, a small unstable set around V, and you can create a local homeomorphism between those two neighborhoods. And the idea now is that the equivalence, the stable equivalence relation on this unstable set, so this unstable leaf of 0, can become a topological space. And the basis for the topology is given by the graphs of those holonomy maps. All right? And you can multiply in this way, so you have WV, VZ, and you can multiply whenever they are in the same stable leaf. So you can move only on the same stable leaf. So you have multiplication, it's closer to being a group, so you can make sense of convolution of functions of that group-like structure, the groupoid. And you can create a Caesar algebra representing this behavior. And this can be done abstractly for Smale spaces, not just only on the torus. You have the stable and unstable equivalencies. You can construct, you can restrict them on transversals. So the stable equivalence, you can always find an unstable leaf in the Smale space, but you can do this restriction and you can topologize those equivalence relations using holonomy maps and consider convolution of functions lead them into stable and unstable algebras. So these stable and unstable algebras encode the stable and unstable foliations for a Smale space. Here's this last slide. In one of the works, my previous works, was to study those stable and unstable foliations for Smale spaces. And the following interesting thing is happening. You can take the metric D on the Smale space and lift it to a metric on these equivalence classes. That's not an obvious thing to do, it's quite elaborate, but it's possible. And these metrics, you want them to respect the groupoid structure, okay? To be compatible with the groupoid structure. And then, since you have a metric space, you can talk about Lipschitz functions, and the algebra of Lipschitz functions of those stable and unstable groupoids. You can enlarge them in a canonical way then to Banach subalgebras of the stable and unstable foliation, Caesar algebras. And the following thing happens. if you consider the commutator, how much stable and unstable elements commute on the same Hilbert space that they act, then you see that all these commutators, they are compact with singular values in LP, with P greater than the house of dimensions. And this is quite important for doing index theory in dynamical systems and computing topological invariants. And I will finish with this. First, I had obtained this. And here I had obtained P greater, so this estimate, this spectrum theoretic estimate, had obtained that holds for P greater than 2 times the topological entropy over the logarithm of lambda. And I didn't know what that was. So I went back to and tried to show that it's the house of dimension. And that's how I ended up in the Ahlfors regularity. And this computation was done purely in spectral theoretic ways. This is, I think, the interesting part. And it can be done really as follows. So you have stable elements. So these are unstable sets, and you move through those red lines through stable holonomy maps. And then you have unstable elements in D, where here you have these these green lines are now stable leaves, and you move through them through unstable holonomy maps. And now, as you iterate the dynamics, these will intersect more and more, and these rectangular neighborhoods created by their intersection, like here, they will become more and more, and you can estimate how many they become after you integrate the dynamics. They increase like that, e to the 2 times the entropy times n. And you can also estimate how small the rectangles become on the stable and unstable set. And this gives you this estimate here. And it happens to be the Ahlfors regularity. So that's all. Thank you.
So any questions or comments?
So did you study this algebras?
Yes, in what sense?
For example, I think that if you take without stable really the action, I think you should have some classification.
Yes.
Stable rank, I think you have one. But do you know if there is
The what? Which one?
For example, stable rank, I think it's one. I think also there are not so many projections.
No, they do have projections, and that's
Okay, but one, maybe one, no?
No.
They have several projections.
Yeah, you can
This is
exist.
strange.
Projections exist.
Many projections.
So if you act also on S and on U, you act with the integers. You apply the homeomorphism.
No, but I'm not talking about stable and unstable. I'm talking about the action on the space.
C of x cross z.
Exactly. I think that there are not so many projections. I think so.
Yeah, maybe.
I don't know.
It depends on the space itself. Also,
Yeah.
if you act on a Cantor set.
Okay, yeah. I mean, if the space is more
Yeah.
than 0 dimension.
Yeah.
yeah, sure.
Yeah.
But do you know if there are any results about the structure of this?
Of these algebras?
Yes.
I wouldn't say, except for the obvious results, like semi-finite.
So we don't know if they are classified.
I would say they are.
Yeah, me too,
But-
but is it written anywhere?
I don't know, like classification of SU and their cross products is done by Karen Strang and Robin Dilly.
The stable and unstable.
Yeah.
Yes.
But classification of C of x cross Z, I think we would follow from general stuff. But definitely you need
Well,
more.
we
You need
should
more.
say some.
Yeah.
I mean, all or you understand the Robin type decompositions, or another way is to study the structure, but there is much information, so it's something that is.
Yeah, sure.
Yeah.
I haven't seen many papers on Axiom per se. Let's put it that
Please
way.
go. Okay, thanks.
More questions? Alright.
Yeah. Thank you. I mean, I already had the questions.
Yeah.